Hey everyone, in this video I'm going to show you how to graph a piecewise function. And you might first wonder what is a piecewise function, and to that I'll answer it's exactly what you think it is. So it's a function, just like f of x equals 2x plus 3 is a function, but you're just going to be viewing a piece of that function, aka a portion of the graph. So you're seeing a variety of functions on one coordinate plane, but just in smaller pieces of that. For example, I actually plugged this particular piecewise function into Desmos. So let's observe what you see here. Okay, so you'll see three different equations. They're all lines. You have a red, a blue, and a green line. But instead of seeing the whole line that stretches forever in both directions, they have distinct stopping points, as you can see here, or you've just seen a portion of the graph. Okay, and a piecewise function is when all of those functions are graphed on the same coordinate plane. They're all working together to create one, unique function looking graph. Okay, so this is a piecewise function, but the question is, how do we do that on our own without Desmos? Okay, so when you see a piecewise function, it'll look something like this. This curly bracket is just grouping those three functions together. For a piecewise function, you could have two different equations, you could have three different equations, you could have 10 different equations, but this one in this case has three different equations grouped together by that curly bracket. And all three of these equations together make up f of x, our function. Okay, so these equations shouldn't look too unfamiliar. This particular equation is kind of like the equation y equals 2x plus 3. This one's kind of like the equation y equals 4. And this one's kind of like the equation y equals negative x plus 8. But then you're given these restrictions. So this one, you're only looking at the x values that are less than negative 1. So essentially what this is here, this is a domain restriction. Okay, domain because you're talking about the x values, and you're restricting from seeing infinite domain to just seeing that piece where x's are less than negative 1. Okay, whereas this piece over here will always be the rule of the piecewise function. That's a u, but it doesn't look like one. There you go. That's the rule. So the equation is the rule, then the domain restriction, that's what a piecewise function looks like. Okay, or you're seeing the equation y equals 4, but you only want to view x's that are in between negative 1 and 4. Okay, or last but not least, you have the equation of the line negative x plus 8, but you're viewing x that is greater than or equal to 4. And these all happen to be lines, but they don't have to be lines, right? They were all lines here. You could do this for parabolas, exponential graphs, whatever it is, you would do the exact same steps. So we're just going to go through a basic example with a linear equation here. Okay, in order to graph this, there's a couple different things you could do. Okay, so let's say I have 2x plus 3, and I know how to graph that because 2x plus 3 is really in y equals mx plus b form, where m, your slope is, m, your slope is 2, and b, your y-intercept is 3. You could come to the graph, and you could plot your y-intercept at 3, and then your slope would be rise 2, run 1. This is a review of Algebra 1, so if you have any questions, let me know, but that's 2 over 1 for your slope. So you'd rise 2, 1, run 1, mouthful, in the positive direction, and you could graph your line that way, if you like. Okay, so let's just kind of complete that here. Rise 2, run 1, you just keep going and going. It goes on infinitely. You get this line, right? I didn't draw that very well, but that's okay. I was going to erase it anyways. Okay. However, for this, you only want to see x values that are less than negative 1. So I'm going to draw a boundary on this graph. Here's negative 1. You only want to see the x values that are less than this. So really what you want is you only want anything to the left of this line. You could graph that portion of the piecewise function and erase the rest. Okay, that's option 1 if you're super comfortable with how to graph that equation. Okay, option 2 is, we won't always know exactly how to graph something. So if you want to graph any function, you can always make a table. So let's keep going, and let's say I wanted to do 2x plus 3, but in a different way. I could say, okay, if I want to plot this, let me make a table. I can plug in some x values and find my corresponding y values. Okay, this may be a better method than erasing because when you make a table, you can use the domain restriction to help. I could only plug in x values that are less than -1. Okay, you will always want to plug in that boundary, so I'll want to plug in -1 to see, where it begins or ends, depending on how you look at it. So if I plug in -1, you have 2 times -1 is -2, plus 3 would be 1. And I could plot that point is -1, +1, which is right here, as you saw in my graph before. And I could keep doing this. I could plug in something like -3. -3 times 2 is -6, plus 3 is -3. And I could go to my graph and plot -3. -3 is right here. And then I could connect the dots to get that piece of the line. Okay, this is just more of a concrete way where you don't have to erase the line. You can just plot strategically to fit the domain restriction. And this is what I'm going to do for the other two pieces of my piecewise function as well. Okay, so we have gotten the first piece. Now I'm going to move on to the second piece, which is the equation like y equals 4. Let's make a table for this. I think this will be a little bit easier. Okay, so for this, I have my x and my y. Okay, y equals 4 is a line, but it's the line where all of your y values are equal to 4. Think about that as a rule. So it doesn't matter what your x is, all of your y values will be 4. Okay, and the x values you want are between -1 and 4. So one of the points would be -1, 4. One of the points would be 4, 4. Another point could be 0, 4, 2, 4, 3, 4, 1/2, 4. Anything that's between -1 and 4. And if you plot that, it's going to look something like this. So at -1, we go up to 4. At 0, we're at 4. At 2, we're at 4. And at 4, we're at 4. And you get a horizontal line, which makes sense because the rule is all your y values have to equal 4. So they're all going to go up the exact same amount on the graph and make a horizontal line. Okay, now, based on what we talked about before, we've looked at domain in the past with the set notation and the inequalities here. You may notice that there are different symbols here. We've got the less than, the greater than, the less than or equal to, the greater than or equal to. And what we remember from our previous learning, hopefully, I should say, is that anytime you have, and let's write this below here actually, anytime you have greater than or less than with no bar below, that just means it cannot be equal to. Okay, not also equal to, just greater than those values. Okay, so it would just be greater or less, which if you remember on our graph associates with an open circle. Because you're not actually including that value, you're just going all the way up to that value. Versus if you have with the line below it, that means it's also equal to. Okay, so it's either greater or equal, greater than or equal to, or it could be less than or equal to. And from our domain and range, we know that that means closed circle. The reason that's closed circle is because it's included, because it's equal to that value, whereas the open circle is not included. Okay, that's old information that I'm summarizing again, so make sure you have that down somewhere. But the reason I'm bringing that up is you do need to take that into consideration on your graph. So let's look at what I've graphed and adjust as needed. In the first example, you had 2x plus 3. For x is only less than -1, it cannot be equal to -1. Okay, so here you see a closed circle. That actually needs to be an open circle because it cannot be equal to that. It's just less than -1. Okay, similarly here, on -1 for the second graph here, you see it's equal to, so that's going to stay closed. But at the 4, okay, it cannot be equal to the 4. It's just less than the 4. Let's see, 1, 2, 3. So at the 4, you would need an open circle like so. Just like we did on our graphs before, you need to include the same rules in piecewise functions. And with that said, we will complete this last graph here by graphing negative x plus 8. My method is going to be to make a table again. Okay, so you want to graph negative x plus 8. Let's get a different color going. I don't know. This was supposed to be purple. Let's fix that. Okay, cool. Now purple graph goes with purple table, and we'll make this green. Sorry to be all over the place here, but I'm making a table for the third equation. Okay, this time you only want x values that are greater than or equal to 4. So we're definitely going to plug in our boundary to see what happens at 4. I'll do that first. So at 4, it would be negative 4, because there's a negative in front of the x, plus 8, which would be positive 4. So then I can go and plot a point at 4, 4. And you'll notice we already have a point at 4, 4. Okay, it's this open circle that was also on that graph, which you saw in my Desmos graph here, is those are actually connected. They're connected right here, which is okay to do. Okay, now since the piecewise function is all connected, this piece connects to this piece, I recognize that the 4 was not included on that horizontal line, but the 4 is included on this piece here. So what really happens at that point is the green graph is going to fill in the purple graph. Since they work together, it fills in the fact that that wasn't included. It fills in the open circle. Okay, now you can plot anything that, again, where x is greater than 4. So I could plot like 5 and 6. So if I plug in 5, it would be negative 5 plus 8, which would be 3. So 5, 1, 2, 3 would be right here. Let's plot negative 6 as well. So it'd be negative 6 plus 8, which is 2. So it'd be 6, 2. And you get a line that looks like this. And it would go on forever in that direction because you want all x values that are greater than 4. There's no stopping point, just anything greater. So I throw the arrow at the end. And this is what that piecewise function would look like. Okay, so you can throw in a Desmos and see what it looks like here, but you can also do it by hand now. Best way to do that is to make a table. Use strategic values that are from the domain. Okay, you can also plot lines like you know how to plot lines or parabolas, but I personally think the easier method is making a table so you can pick those specific values. And that's a piecewise function. It's a function where you're just looking at a portion of a graph or 2 or 3 all on the same coordinate plane, and together they make up one larger function. Okay, probably the most challenging part is this piece here where the green graph kind of filled in the point that wasn't included. So if you have any questions about that, please definitely let me know. Otherwise, that's all I have for you, and have a good rest of your day.